Yep. They're resurfacing the road. So what they do, they take the old tar, they dig it out. You see that belt, it goes on this machine, it goes on the belt, and it pours into the truck. Well, if you watch in the sand the truck pour, it will look like this, just like if you have, the belt looks like this, and all the sand falls off it. You'll see a shape that looks like a cone upside down. A lot of times you want to know how fast the volume is changing in relation to the radius or the height. That's what related rates is. If the height changes at the rate of 1 inch per minute, how much the volume change per minute? That's what this topic is. So a volume for a shape like this, that's a cone. You can look in the back of the book. It's 1/3 pi r squared h. You don't have to memorize this equation, but if you look in the back of the book, you'll find these shapes here. Yeah, the last page too in the book there. Pi r squared h over 3. That's the right circular cone right there. A sphere is 4/3 pi r cubed, the volume, right here. So all the shapes, the book has a picture. You can always just go, even on Google, if you were to find something you're not sure what it looks like, they'll tell you what the equation for it. The circle is pi r squared. So now I'm trying to find out how fast the volume is changing. Well, the volume is going to change depending on how fast the radius and the height. So when you take the derivative, now all of these, the derivative is going to be with respect to time. So what's the derivative of v? dv dt equals 1/3 pi is a constant that sits in the front. What's the derivative of r squared h? Well, that means r squared times h. So what method are we going to use? Product rule. The first, which is r squared, times the derivative h, and the derivative h is going to be dh dt, plus h times, what's the derivative r? I mean r squared. 2r times what? dr dt. So for those people who had a hard time with implicit differentiation, maybe this will cement that in your mind. We always want to take it with respect to dt. So dx dt, dy dt, dh dt. Before it was dx dx. We didn't have to write it. So when you clean that equation, it says the volume is going to change at the rate. That's the rate, how fast, per minute, per second. Following that equation, you tell me what the height is. So that'll be r squared dh dt plus 2rh dr dt. That is what related rates are. Let's put some numbers in them and show you how they work. Let's say you got a new basketball or a balloon, whatever you want it to be. The basketball or the balloon has a shape that looks like a sphere. That's the basketball in 3-dimensional. I'm horrible. That's supposed to be a 3-dimensional basketball. The volume of a basketball is 4/3, or a sphere, 4/3 pi r cubed. That's the equation for it. The volume. The back of the book. Let's look at this problem. An air is being pumped into a balloon. So we're adding air to the balloon. If you're adding that, that's a plus. If it's leaking out, that's what? Minus. You have to pay attention to plus or minus. An air is being added to a balloon at the rate of 4.5 cubic feet per minute. Added at the rate of 4.5 cubic feet per minute. Now let's stop and think about this number. Could that number be r?
Yes.
Let's try again. Could that number be r? No. Good answer. No. Why not? R is the radius. What's the unit for radius? If you were to measure the radius of a sphere, you take your ruler, go, that's 4 inches, not 4 inches cubed. What's a cube then? Volume is the cube. Area is the square. So just from the cube here, that tells you that's the volume. Now, when you blow a balloon there, you go, initially the balloon is small. When you blow on it, it gets big. But once the balloon is big and you blow on it, guess what? It's not really moving that much because the volume is so big. So that air that you put in now in a big volume is really nothing, but in a small, when you have a small balloon there, you blow on it, it's going to get bigger quickly. But when you get really big, all that air you're putting in gently moving the edges of the balloon. So it depends what time you look at it. It says the air was being added at the rate of 4.5 cubic feet per minute. Find the rate of change of the radius. What's dr dt? When the radius. So what's that? Question mark here. When r equals 2 feet. How fast the radius is increasing. 2 feet is actually a good size sphere there. So when you blow on it, it's not really going to move that much. But let's see what the equation is. Let's take the derivative of that. The derivative of v is what? Everything with respect to time here. dv dt. Now, 4/3 pi is a constant. What's the derivative r cubed? 3r squared. Go ahead, you're not done. dr dt. So the volume is changing at the rate of, if you clean that, will be 4 pi r squared dr dt. That's how fast the volume is changing with respect to the change in the radius. Now plug in the numbers. Do we know what dv dt? 4.5. 4 pi. Do we know what r is? 2 squared, that's 4. dr dt. Can we solve for dr dt? $4.5 divided by what? 16 pi? Calc. Oh, I guess I didn't use my calculator yet. $4.5 divided by 16 divided by pi. The radius is only changing at the rate of 0.09 feet per minute at that time. Because it's a huge ball. We're talking about a ball this big, a balloon. It's like a medicine balloon, you're blowing into it. It's not going to change that fast at that time. Yes?
Oh, wait, never mind.
Sure?
Yeah, I was wondering where that 3 went, but I just...
Cancel that 3. So that tells you when you're blowing air into it at the rate of 4.5 cubic, that's by a lot of air, cubic feet of air per minute. Just like if you try to blow up some of these flotation for the pool, and that thing is like not going. By the end of the day, you're dizzy and all this stuff. Because it's a big container. You're putting this much air each time. Your lungs, if you're healthy, your lungs are the maximum 4 liters per blow. That's because I know that when I had my open heart surgery. They bring me this instrument and says, okay, I want you to blow on this and see how much. And I go, and I got it to 0.5 liter. Now, my son comes in, like I was curious, like, Joseph, blow on this, let's see how much. He goes, and it goes to 4. I go, oh, you can't actually go to 4. That became my mission because the closer I get to 4, I get to go home. At 1 o'clock in the morning. At 3 o'clock in the morning. I'm blowing, I'm walking, I'm blowing, I'm walking. I was walking 4 miles. The day after my surgery, I walked 2 miles. The second day, I walked 4 miles. I was determined I'm going home quickly. And third day, they sent me home. I managed to get to 2.7, almost 3 cubic in 2 days. So he goes, yeah, you're healthy. You can go home now. because you can actually, your lung can hold up to 4 cubic liters of air.
How long ago was that?
My open heart surgery was 3 years ago, May 24th. I was working out and I had a dizzy spell and I almost died. I shouldn't really be here, but I had a defective valve. I wasn't unhealthy. I had a valve with me. I never knew anything about it. Nobody ever knew anything about it till it happened. They go, you need an open heart surgery. When? ASAP. In 2 days. My heart was completely shut down, like going like this when I was working out. Yeah. Just lucky for me. I had the surgery April 24th. I was teaching summer school May 1st. I was determined I'm not taking a day off from work. And I never took. The president came to me and goes, Z, how many sick days do you have? I go, about 2.5 years. I've been here, I finished 31 years. Did not take one sick day yet in 31 years. I get 2 personal days every year, actually 3, and I do not even take them. They expired. Last year did not take 1. The year before that did not take any. I like working. I said, I'm not planning on missing. I said, take some time off. I go, nope. We have insurance. That's why. I go, nope. I'll be there. I was stubborn. Nope. And I was here working, but my job is easy. Like if you have an open heart surgeon, you got to sit here, it's not bad. But if you're construction, you couldn't do anything because I couldn't pick more than 2.5 pounds. That's my limit of weight.
I'm just curious as to why it's not expanding it in cubic feet. It's only expanding.
Well, you're talking about the radius.
Oh, okay.
The radius, right? Not the volume. Let's talk about the speed of airplane. I like that. There's a plane. An airplane is flying on a flight path that will take it directly over the radar. Radar is down here. This is the building. This is the radar. It's going to fly over it. So it's not landing. It's going to fly over Bradley Airport. As shown in the figure. Okay. The height of the plane is 6 miles above the radar. So this is 6 miles. 6 times 5,280 feet. At 32,000 feet high. When you fly to Orlando, that's where you're flying at, 33,000 feet. So 6 miles high, you're up in the sky. Okay. If S, that's the distance to the radar, they call that distance S. If S is decreasing at the rate of 400 miles per hour, so ds dt, decreasing, what does that mean? Minus. What was it, 400? 400 miles per hour. When S equals 10. What is the speed of the plane? If I call this distance x, and I get up a little bit of physics in it. Physics is what? Speed is what? Distance over what? Time. So really the indirect way, what's the speed? Here, they're asking for dx dt. They're just being cute about it. When they say, what's the speed? What they're asking, what's dx dt? If you never had physics, you go, huh? But that's actually what they're looking for. So now I got to find an equation that has s and x in it. They don't give us an equation here. Well, what do you notice about the picture I drew there? Triangle, very good. Can you see the triangle? I'll color it pink. Pretty color pink, here we go. What kind of triangle we have here? Right triangle. What do we know about right triangle? Pythagorean theorem. right? So s squared equals x squared plus 6 squared. So now I have an equation that ties s and x. See, when they give you s, ds, dt, they're looking for dx, dt. Your first job is to find an equation that ties them together. In the previous ones, they gave you that equation. They told you the story. Here, you got to write that equation yourself. That's an equation that ties s and x. So s squared equals x squared plus what? 36? Now let's take the derivative. What is the derivative s? I mean s squared. 2s, keep going, times what? Or ds dt. Let's just write ds dt. It is, but let's just put ds dt. What's the derivative of x squared? 2x times what? dx dt. What's the derivative of 36? I can divide both sides by 2, right, to shrink it. S times ds dt equals x times dx dt. Now plug in the numbers. We have a little problem. We don't know what x is. It says, what is dx dt? So let's go plug in the numbers here. S, what's S? 10. What's ds dt? Negative 400 equals, what's x?
Plug it into your diagram.
Ah, very good. We don't know what x, but we can find it. We know this is 10. We know this is 6. Can we find what x is? Pythagorean theorem. 10 squared equals 6 squared plus x squared. 100 equals 36 plus x squared. X squared equals 64. X equals 8. So now you put an 8 here times dx dt. Can we solve for dx dt? Is that negative 500? I think it's negative 500. It means that distance shrinking, getting less and less. So the speed of the plane is really 500 miles per hour. The negative is, it says it's shrinking. It's coming over this because we're talking x is the distance from here to directly above the radar. And that distance is shrinking, decreasing at the rate of 500 miles per hour. That's the speed of the plane. Let me try another example.
See, how did you get negative 500?
10 times negative 400. That's negative 4,000 divided by 8.
Oh, all right.
Right? Is that 500? I just assume it's 500 in my head. Yeah.
Amazing what altitude does to airspeed, huh?
Oh, yeah. Absolutely. The wind there, you're flying up there, you can pick up 40, 50, 60 miles per hour easily. My daughter's coming from Jordan tomorrow. She's been studying abroad there for 5 weeks. Her trip to Jordan was a little bit less than 11 hours going in. Tomorrow will be 12 and a half hours coming back. So it adds 2+ hours to her trip. That's because of the wind. You know? And the higher you go, the faster the wind. So when you really want to get there fast, if the pilot is running behind on time, they climb really high. Instead of 33,000 feet, they ask permission to go to 40,000 feet. The jet stream is flying there, extremely faster. So you get there faster. That's why when they go from here to, let's say, to, you want to go to Washington, D.C., they're not going to go that high because by the time you get to that height, you're already over Washington, D.C., you know. But they like to go high as they can. A long trip, they want to go as high as possible, up to a limit, so you can actually pick that jet stream. On the way back, you want to be as low as possible because the wind is less. I have all these numbers. I used to fly a single engine plane. It tells you all the stuff per 1,000. For the temperature drops 2 degrees per 1,000 feet. Every time you go up to 1,000 feet, temperature drops by 2 degrees. So when you're flying at 33,000 feet, that means the temperature is 66 degrees below what we have on the ground. That's why it's amazing when people hide in the wheel of the plane, like that kid who just did to Hawaii. You know, if the temperature is 40 degrees on the ground, especially winter time, subtract 60 degrees, 70 degrees from it, he's minus 30 degree up there. You know.
Amazing how he survived.
Oh yeah. Well, he was that person. He was actually when he came out. He didn't know where he was. He was just completely out of it because lack of there's no oxygen there either at that height. It's amazing. Sometimes it's not your day. You shouldn't be alive. Actually, to be honest with you, you pass out completely. That's why I tell people if you're flying and something wrong with the plane, don't worry. If there's a hole in the plane, you won't even know it. You'll pass out in 30 seconds. That's how it takes, 30 seconds, you're gone. So when the plane crashes, you won't even know it. You out. That's the good side of it. You don't want to be awake for 6 miles thinking about the head in the ground. So I'd rather be out. Changing the angle of elevation. I love these videos with the stories on them, huh? People are like, what is he talking about? Find the rate of change of the angle of elevation of a camera. So we have the spaceship taking off here again. Same problem. Different story here. I don't know if you remember a golfer named Payne Stewart. He had his private jet, and they lost oxygen, and the mask came down. They didn't have enough time to put them on. They all passed out. And the plane was flying on autopilot with 6 people in it, all asleep. So now the U.S. sends a plane because it's going to hit a city, it's going to run out of fuel and land over Denver. So they put F-15 next to it to see what's going on. They tried to talk to him. He wasn't talking. They come close. They look. They all passed out because the oxygen mask is dangling, but nobody has them on. You got 30 seconds. Right before actually it landed, the plane came, put the wing under the other wing, and tipped that plane sideways to go away from Colorado to crash into the mountain, so it doesn't kill anyone.
Don't the oxygen tanks, they don't have a lot of oxygen anyway, like a minute or two?
Oh no, they have plenty. You have plenty of time. Yep.
Question, by that logic, couldn't they have tried to lower the plane a little?
Oh, you can't. No. Land the plane. There's no way. With
No,
no
I
part.
mean, like, with the wing of the jet, couldn't they have went at the plane's tail and tried to nudge it up a bit to lower it so that way one of them may have regained?
Well, they already passed out. They're gone. Because you don't have that much time before you pass out.
No,
When
I
you
mean,
fly.
like, couldn't they have, if there was more of an oxygen-rich environment at a lower altitude?
Yeah, 16,000 feet. That's when the oxygen starts. 15,000 actually. Usually they shoot them with just go behind them with the missile and they blow them out of the sky. That's the safest way, the humane way of doing it actually. Doesn't sound humane.
It does.
Yep.
That doesn't sound humane to me, but sounds logical, I guess.
Just like when you see a deer on the side of the road that's injured, the humane way is shoot him and kill him. You know? I don't hunt, but just telling you they're going to be dead. Why kill other people? Okay, we're going to find an angle theta here. Okay, let's see what we know. Find the rate of change of the angle of elevation of the camera. We're looking for d theta dt. That's the picture I took from the book. At t equals 10 seconds after liftoff.
I think it says 2,000 on the bottom.
2,000?
Yeah.
Is it? I don't know, I see some zeros. I can't focus on them. I try to focus, but... So we're not sure how fast the plane is moving or what that distance is. Because we need to know what that side is. So what should we call that side? The height? we have opposite. We have, by the way, to find the height, what's the question here? D theta, okay. Do we know how fast the plane is taking off? That, oh, they give us the equation for S. They call that S the height. I'm saying something is missing. That rocket is going up there at this, the equation for the distance, S equals 50t squared. That wasn't listed in the problem until you get to the solution. I'm looking like something is missing here. They call that S the height, 50t squared. So now we have an equation that will tie S and the 2000 theta. What's that equation? Is it tangent? Now, we need d theta dt. I don't want the tangent. So one way to fix it, you take the arctan, right? Of tan theta. Arctan of S over 2000. Arctan of tan, they will cancel each other out. And now I came up with my equation for theta. Theta is equal to arctan S over 2000 So here's my u. I'm going to take the inverse tan, the derivative now. U equals S over 2000, which I can write 1 over 2000 times S. What's the derivative of that? 1 over 2000 times the derivative S, which is ds dt. Well, if S equals 50t squared, do we know what ds dt, the derivative of that? $100t. So instead of ds dt, let's put 100t here. And when we do the math, is that t over 20? I think it's t over 20, u prime. Instead of s here for u, actually, maybe we'll replace s with 50t squared. So what is u equal to? Instead of 1 over 2000 s, let's replace s with 50t squared. That'll be t squared over what? What's 2000 over 50? Is that 40? Notice, just take the s out, put 50t squared. Now I'm done. The derivative of this, d theta dt, equals derivative of this, that'll be u sub prime over 1 plus u squared. What's u sub prime? T over 20, 1 plus t squared over 40, and you're going to square it. And the question, they wanted at t equals what, 10 seconds? At t equals 10, that's a half. 1 plus, bless you. 10 squared is what? 100. 100 divided by 40, is that 2.5? 2.5 squared, is that 6.25? I think it's 6.25. So it's 0.5 over 7.5. Is it 115? I think it's 115.
0.5 over 7.25, right?
7.25, yep, thank you. It's not 115 then. 7, what's that, 14 me? 14? 14.5. Yep. And whatever that number is, 1 divided by 14.25,
229.
2 over 29, yep. I was looking for a decimal number, but I'll take 2 over 29.
0.0689655672.
Very good. Point, was it?
It's like 0.0689.
0.7 is good. Yep.
0.27.
So the angle is changing at the rate of 0.07 radian per second. Radian per second. That's how fast that angle is rising at that time. That's section 3.7. Now let's do the last one. Definitely need a calculator for the last one. Definitely.